lecture 29. Today we will be discussing about the Nilradical and Jacobson radical of a ring. So, let us start. Previously, we have discussed about the zero divisor and nilpotent elements in a ring. So, let us quickly recall the definition of nilpotent element first, and then we will define the nilradical. So, what was the nilpotent element? So, a nilpotent element, if you remember, was an element. So, let R be a ring. So, let R be a ring. An element X in R is called nilpotent if x to the power n is equal to 0 for some n strictly greater than 0. So, if you have an element such that the element need not be always 0, of course, if 0 satisfies this condition, so 0 is always a nilpotent element, but if there is some non-zero element such that its power is 0, then we call that element to be a nilpotent element. So, this we have already seen. Now, we will be defining the set. Let us denote n of R. So, this is the collection of all elements. So, all x in R is the collection of all elements in R such that x to the power n is equal to 0 for some n positive. That means n of R is nothing but the set of all nilpotent elements of the ring. So, this is nothing but the set of all nilpotent elements of the ring R. Then we can ask one question that whether this set of all nilpotent elements forms a ideal and or not, and we will see that in fact this set forms an ideal. So, the first thing that we would like to prove is the following theorem, which says that n of R is an ideal of R, and not only that, if you consider the quotient ring R quotient n of R, then in this quotient ring there will be no non-zero nilpotent elements, because we are actually going modulo all the going quotient by the n of R, which is the set of all nilpotent elements. So, in R quotient n, this quotient ring has no non-zero nilpotent elements. So, this is what we will be proving first. So, first let us try to show that this nilradical, this n of R, that is the collection of all nilpotent elements, forms an ideal in the ring R. So, in order to show that this set forms an ideal, we will start with an element, say x in n of R, and so then we will show that if I multiply this x with any element from this ring, then again it will be a nilpotent element. So, for example, since x is in the x is in the set of all nilpotent elements. So, this implies that x to the power n is 0 for some n positive. And let us consider that any element a in R, then if I consider ax and raise it to the power n, since our ring is commutative ring, I can write it as a to the power n into x to the power n, and hence this is nothing but equal to 0. So, this implies that ax belongs to n of R, because some power of ax is again 0. So, that means ax is a nilpotent element. So, it is closed under multiplication from the elements of the ring. Now I will show that if I take two elements, say x and y, in this set n of R, we want to show that their addition will also be in this set. So, in order to show that, since x and y are nilpotent elements, this implies that x to the power n will be equal to 0 and y to the power m will be equal to 0 for some n and m positive. So, now I would like to show that x plus y will be a nilpotent element. So, for that, you observe that x plus y to the power n plus m minus 1, if I consider, then this is, if I expand in binomial coefficient, then this is nothing but n plus m minus 1 choose I of x to the power I into y to the power n plus m minus 1 minus I is from 0 to n plus m minus 1, where this n plus m minus 1 choose I are the usual binomial coefficients. So, this much we know. Now, I would like to show that this x plus y to the power n plus m minus 1 is in fact coming out to be 0. So, why is that? So, if my I is greater than equal to n, then in that case x to the power n will be equal, x to the power I will be equal to 0. Sorry, x to the power I is equal to 0. So, for all I greater than equal to n, x to the power I is 0 because x to the power n is 0. So, all those coefficients when I is greater than equal to, all those elements where I is greater than equal to n, for those x to the power I will be equal to 0 in this expression. And if my I is strictly less than n, in that case I can write down my n plus m minus 1 minus I as m plus n minus 1 minus I, but since I is strictly less than n, so this thing will always be positive and hence this will be less than equal to m, and which imply that y to the power m plus n minus 1 minus I will be equal to 0 as y to the power m is equal to 0. So, this will be for all I strictly less than n, this quantity is equal to 0. So, then in this expression I can see that either x to the power I will be equal to 0 whenever I is greater than equal to n, and for the remaining when I is strictly less than n, then this quantity will be 0 in this summation. Therefore, x plus y to the power n plus m minus 1 is coming out to be 0. So, this implies that x plus y to the power n plus m minus 1 is equal to 0, which says that x plus y belongs to n of R. So, x plus y is again a nilpotent element. Therefore, it is closed under addition operation. That means that this is an ideal. Hence, that n of R is an ideal of R. So, we have proved that the set of all nilpotent elements forms an ideal in the ring R. Next, we will prove that in R quotient NR, there is no non-zero nilpotent element. So, let us consider an element, say x bar, in this quotient R quotient N of R. So, this represents the residue class of x in this quotient ring that I am denoting by x bar. So, let this x bar be a nilpotent element, be an nilpotent element in the quotient ring, in this quotient ring. So, that implies that some power of x bar should be equal to 0. So, x bar to the power n is equal to 0 for some n positive. So, this means what? That this is 0 in where? So this is 0 in R quotient in R. So this is 0 bar, I should say. So this is 0 bar means that x to the power n is in the set n of R. So that means x to the power n is a nilpotent element. So which implies that x to the power n to the power m will be equal to 0 for some m positive, as x to the power n is nilpotent. So this says that x to the power nm is equal to 0, which implies that x is in fact a nilpotent element. That means x belongs to this set n of R, that is x bar is equal to 0. So it says that if I start with an element x bar which is a nilpotent element in this quotient ring, then that element x bar is coming out to be 0. So that means there is no non-zero nilpotent element in this quotient ring. This completes the proof of this theorem. So now we will see some interesting results about this. So before doing that, let us define. So this set of nilpotent elements has a special name. This is known as the Nilradical of the ring. So the ideal n of R is called the Nilradical of R. So if you start with any ring and you consider the set of all nilpotent elements, it forms an ideal, and this ideal is called the Nilradical of the ring R. Now we will prove that this nilradical can be actually viewed as, we will prove in fact that this nilradical is nothing but the intersection of all the prime ideals of the ring. So the next proposition gives another characterization of the nilradical. That means the set of all nilpotent elements is nothing but the intersection of all the prime ideals. So this says that the nilradical of R is the intersection of all prime ideals of the ring R. So the nilradical is nothing but the intersection of all the prime ideals of this ring. So how to prove this? So we would like to, let us consider n prime to be the intersection of all prime ideals. So let n prime denote the intersection of all prime ideals of the ring R, and we would like to show that the nilradical of R is equal to n prime. So I will prove that this n of R is contained inside n prime, and conversely n prime is sitting inside n of R. So first let us start with an element x in the nilradical of R, and we would like to show that x is in n prime. That means x is in the intersection of all the prime ideals. So since x is in the nilradical, this implies that x to the power n is equal to 0 for some n positive, but 0 belongs to every prime ideal. So that means that x to the power n, which is equal to 0, belongs to P for all prime ideals P of R. So x to the power n belongs to P, but since P is a prime ideal, that will imply that x belongs to P, as P is a prime ideal. Therefore, x to the power n belongs to P implies that x is in P. So So that means X is in P for all the prime ideals of R, therefore X will be in the intersection of all the prime ideals. This proof says that X belongs to N prime. So this proves that this nilradical is contained inside the intersection of all the prime ideals. Now, in order to prove the other containment, I will prove that if you start with some element which is not in the nilradical, I will prove that that element will not be in N prime. So, to prove the reverse containment, that is N prime sitting inside in the nilradical, we show that if F doesn't belongs to the nilradical, then F doesn't belongs to N prime. So this is by proving this, we will be able to prove this other containment in here. So let us start with an element F which is not a nilpotent element. So suppose that F is not a nilpotent element. Now I will consider the set sigma. So let sigma be the set of all ideals I with the property that for all n greater than 0, f to the power n doesn't belongs to I. So I have started with one element f which is not a nilpotent element. Now I am constructing this sigma to be the collection of all ideals I such that no power of f to the power n is in I. That means for all n greater than equal to 0, f to the power n doesn't belongs to I. So this sigma is a collection of ideals such that no power of this particular element f doesn't belongs to I. So if I consider this set, then you can see that this set is non-empty. Why? Because 0 belongs to this set, because I have this particular element f such that f to the power n f to the power n is not equal to 0. So sigma is non-empty as 0, the ideal 0 belongs to this set sigma. Then we will be using the Jones lemma, and Jones lemma says that the sigma will have a maximal element. So I have constructed this set sigma. I have shown that this sigma is non-empty. Then by Jones lemma, Jones lemma applied to the set sigma ordered by inclusion, we can say that sigma has a maximal element. So we have applied this Jones lemma under inclusion on this set sigma, and therefore we have a maximal element in sigma. So let P be the maximal element of sigma. So let P be the maximal element of sigma. And we will prove first that this P is in fact a prime ideal, and we will show that this F doesn't belongs to this particular prime ideal P, and hence it doesn't belongs to the intersection of all prime ideals. So wants to show, we would like to show first that P is a prime ideal. So, the maximal element of this set sigma is a prime ideal. That is our first goal. So, in order to show that P is a prime ideal, I will start with two elements, say x and y, such that they doesn't belongs to this ideal P, and we will show that their product also doesn't belongs to P. Then I consider the ideals P plus x and P plus y. So, of course, since x and y doesn't belongs to P, so these will be strictly, these ideals P plus x and P plus y will be strictly bigger than P, and this will contain this ideal P. So, then these ideals, these P plus x and P plus y will contain the ideal P, and hence they are strictly bigger than, so, and P is a maximal element, therefore these two ideal doesn't belongs to the set sigma. So, they contains P, and therefore this x P plus x and P plus y doesn't belongs to the set sigma. So, if they doesn't belongs to the sigma, that means some power of f will belongs to P plus x and some power of f will be in P plus y. So, then it follows that some power, say f to the power n will be in P plus x and f to the power m will be in P plus y for some n and m positive, n and m positive. So, then note that from here we can conclude that if I consider f to the power n plus m, then this will be in the ideal P plus xy. So, this belongs to P plus xy, hence that means that this ideal P plus xy doesn't belongs to sigma, because sigma is the collection such that no power of f will be in that set, but here f to the power n plus m is in this ideal, therefore this doesn't belongs to this set sigma. And from here it is clear that x y doesn't belongs to P, because if xy belongs to P, then that will imply that P plus xy will be in P, and then P will be in, then this will say that this P plus xy will be in sigma, which will be a contradiction. Therefore, xy doesn't belongs to P. Hence, we have proved that this is a prime ideal. So, we have proved that the maximal element of this set sigma is a prime ideal, and therefore, we can say that, so hence we have found, hence we have a prime ideal P such that f to the power n doesn't belongs to P for all n positive. That means no power of f to the power n belongs to P. So, that will imply that f also doesn't belongs to P. So, we have proved that we have found one prime ideal such that f doesn't belongs to P. So, therefore, f doesn't belongs to n prime, because n prime was the intersection of all prime ideals, and I have found one prime ideal which is nothing but the maximal element of this set sigma, such that f doesn't belongs to this prime ideal. Therefore, f doesn't belongs to n prime. Hence, it proves that this n prime is sitting inside nil radical. Therefore, that nil radical of R is nothing but the intersection of all the prime ideals of the ring R. So, if this is a clear characterization of the nil radical, which says that it is nothing but the intersection of all the prime ideals of the ring. So, once this characterization is over, then we can define another set which is known as the Jacobson radical. So, what is a Jacobson radical? So, the Jacobson radical of R is defined as the intersection of all maximal ideals, of the ring R and is denoted by J of R. So, Jacobson radical is in fact the intersection of all the maximal ideals of ring. So, nil radical was the intersection of all prime ideals. Therefore, this nil radical is sitting inside the Jacobson radical, as every maximal ideal is also a prime ideal. So, we can since all maximal ideals are prime ideals, so it is clear that the nil radical of R is sitting inside the Jacobson radical of R. Then we will give one characterization of the Jacobson radical. So, the following proposition says that an element is in the Jacobson radical if and only if 1 minus xy is a unit in R for all y in R. So, this characterizes that when an element will be in the Jacobson radical if and only 1 minus xy is a unit in the ring for all y in R. So, let us try to prove this first. So, first I will start with that x is this side, that means x is in the Jacobson radical. We will show that 1 minus xy is a unit. So, suppose that 1 minus xy is not a unit. So, if it is not a unit, that means it should be sitting inside some maximal ideal. So, then 1 minus xy should belongs to some maximal ideal M for some maximal ideal M. So, if it is not a unit, then it will be sitting inside some maximal ideal M of the ring R. But I am having that x is in the Jacobson radical. That means x is in the intersection of all maximal ideals. Therefore, particularly x belongs to M also. So, which is in M also. Therefore, I am having now 1 minus xy is in M and x is in M. So, this will imply, which implies that 1 belongs to the maximal ideal M. But maximal ideal is always proper. So, unit element cannot be. So, which is a contradiction. Hence, our assumption is false. That means 1 minus xy has to be a unit. So, now we will prove the converse part. So, for that, let us suppose that X doesn't belongs to M for some maximal ideal. For some maximal ideal M, that means X is not in the Jacobson radical, then we will show that 1 minus xy will not be a unit in this case. So, if X is not in this maximal ideal, then if I add this ideal generated by X with the maximal ideal, then it has to be an ideal which should be strictly bigger than M, but M is a maximal ideal, therefore, this ideal has to be the whole ring. So, if this is the whole ring, then it implies that for some u in the maximal ideal, I should have u plus xy is equal to 1 for some u in M and for some y in R, which implies that 1 minus xy which is equal to u, which is in maximal ideal. Therefore, this is not an unit, and hence 1 minus xy is not an unit. So, we have proved that if you start with an element which is not in the Jacobson radical, then 1 minus xy is not a unit. So, this completes the proof of this characterization of the Jacobson radical. Now, I will define one more term which is known as the local ring. So, a ring with unique maximal ideal is called a local ring. That means in that ring I have only one maximal ideal, there is no other maximal ideal. In fact, you can check that as an example in the power series ring over the field of real numbers. So, this power series ring is a local ring with unique maximal ideal, the ideal generated by X. So, this is an example of a local ring where we are having only one unique maximal ideal. So, with this, today I will stop my lecture, and next time I will give you some examples of Nilradical and Jacobson radical in some rings. So, these are the references that I have used for today's lecture, and thank you.